Hello everyone, this is Shravani Patil. Today in this video, I'll be presenting on the research paper, Research on Cloud Computing Technology Graph Analysis. So let's begin. Introduction to Cloud Computing. Definition. Cloud computing is the on-demand delivery of IT resource like computing power, storage and database over the internet with pay as you go pricing. Service models. Infrastructure as a service provides a virtualized computing resource over the internet. Platform as a service provides a hardware and software tools over the internet. Software as a service delivers the software application via the cloud. Importance. Cloud services enables business to scale rapidly, avoid un- upfront infrastructure cost, and assess resource flexibility. Graph theory overview. Definition. Graph theory is the study of graphs, which are mathematical structures used to model pairwise relationship between objects. Key components. Vertices that are also known as nodes represent entity. For example, device, data centers, edges, also called links, presents the connection between two nodes. For example, network paths. Matrices in graph theory. Degree. Number of edges incident to the vertex. In closeness centrality measures how fast the node can access other nodes in the network. Betweenness centrality measures the influence of node in the communication path between the others. Cloud computing and graph theory intersection. Graph application in cloud. Network topologies. Representing the cloud data centers as a graph structures to a model data flow and communication. Service dependency modeling. Cloud applications are independent and graphs can be captured. These independency on optimization. Dynamic cloud networks. Cloud resources are dynamically allocated and distributed across various data centers. Graph models helps optimize and manage these movements and connection efficiently. Graph processing techniques in cloud environment. Scalability in cloud. Cloud platform provides elastic computing, which is essential for handling massive graph data and processing workloads. Frameworks for graph processing. Apache Graph, a large-scale graph processing frameworks built in Hadoop. GraphX, part of Apache Spark, which handles both graph and data parallel computation. MapReduce, distributed processing of large-scale graphs for operations like PageRank and shortest path calculation. Challenges. Data partitioning, dividing a graph into manageable subgraphs while minimizing communication between partitions. Load balancing, efficient distribution of computational tasks across the cloud service. Anomaly detection using graph analysis in cloud. Anomaly detection in cloud networks. A graph can help to identify unusual patterns in the cloud infrastructure, such as irregular traffic, network instructions, and bottlenecks. Approaches. Knowledge graph. Leveraging graphs database to model complex relationship between cloud components, allowing for anomaly detection using AI techniques. Machine learning techniques using cluster decision making tree or random forest for anomaly detection within the cloud systems. Case study. Detection of distributed denial of service attacks using graph centrally metrics. Fault tolerance and performance optimization. Fault tolerance in cloud. Graph clustering by grouping highly connected nodes that are service or components. The system can isolate faulty nodes and maintain service availability. Replica placement, ensuring that key data is replicated in the multiple location based on the graph analysis to prevent single point of failure. Performance optimization. Graph-based load balancing and resource allocation algorithms helps the cloud systems to minimize latency, optimization bandwidth, and avoid bottlenecks. Graph-based cloud optimization. Resource allocation. Graph helps allocate cloud resource efficiently by modeling the relationship between task, resource, and network bandwidth. Use case optimizing tasks of offloading in edge cloud computing environments using graph based heuristics. Workload distribution. Graph algorithms are used to distribute workload dynamically based on real time networks and task dependencies, which helps balance the load across the different cloud services. Bandwidth management. Allocating bandwidth for distributed application through graph-based predictive modeling. Emerging trends in cloud graph analysis. Graph neural networks. GNNs combines the power of deep learning with graph theory, useful for capturing complex relationships in cloud-based systems. For example, GNN can predict the future states of network traffic or cloud resource usage based on the historical pattern. AI-driven graph analysis. AI techniques are integrated with graph theory for predictive maintenance, resource optimizations, and security anomaly detection. Real-time graph processing handles a live data stream in a cloud with frameworks like Apache Flink and streaming graph analytics. Real-time process enables instant detection of issues like sudden spike in traffic or a latency. Conclusion and further outlook. Summary. Graph theory plays a critical role in the cloud computing by providing models for optimization, anomaly detection, and fault tolerance. Key takeaways. Cloud environment can be modeled as complex graph for efficient resource management and real-time decision making. AI and advanced graph techniques like GNN are pushing the boundaries of cloud computing efficiency and security. Future further research. Research will focus on improving scalability of the graph processing algorithms in cloud platforms and dependency AI integration for enhanced cloud intelligence and automation. Thank you. Hope this video was useful to you all.